This is the beginning of a new playlist I like to call Special Topics. So, under this playlist, I'll attend to some topics that may not have been covered in other playlists previously, or that maybe some one-off topics that I think I could just deal with once and for all, and they do not fit into. Maybe they even fit into other playlists, right? But then they are just special for some special people based on special requests and everything. So I'm doing the very first one for someone I call my school mommy, and and this is about discontinuous Galerkin finite element method. Discontinuous Galerkin finite element method. So in case you have a request in the future and I have time, I may be able to pull it up for you, and that this will be part of this special topic. So let's go ahead and see what this is like. Discontinuous Galerkin finite element method. I remember I've treated finite element method, finite volume method, and all of this under under numerical analysis on the path for partial differential equations. So I remember doing that in the past. So well, here let's look at the discontinuous Galerkin finite element method. So if you want a topic for that, that'll be something like from local polynomial approximation to numerical fluxes, stability, and high order PDE solvers. So let's talk about the learning objectives. By the end of this lesson, you should be able to explain the basic idea behind the discontinuous Galerkin finite element method, explain why the numerical solution is allowed to be discontinuous between elements, construct a discontinuous finite element approximation, derive the discontinuous Galerkin weak formulation, understand jumps, averages, and numerical fluxes, derive and implement the upwind flux, construct the discontinuous Galerkin method for the one-dimensional advection equation, derive element mass and stiffness matrices, understand the method of lines formulation, implement a basic discontinuous Galerkin solver in Python, then understand CFL restrictions and numerical stability, explain the relationship between discontinuous Galerkin and finite volume methods, understand discontinuous Galerkin methods for nonlinear conservation laws, and understand the basic idea of interior penalty, discontinuous Galerkin for diffusion. Then perform convergence and error analysis. Now let's go ahead and deal with this one after the other. First of all, what is the discontinuous Galerkin method? So the DG finite element method is a numerical method for solving partial differential equations. So this could have easily continued under the differential equations playlist. So it combines ideas from finite element methods, finite volume methods, numerical fluxes, high order polynomial approximation. Now, the key feature is that the approximate solution is allowed to be discontinuous between neighboring elements. So that's the key feature, that approximate solution is allowed to be discontinuous between neighboring elements. So for an element k, for instance, we can write u sub h slash k of x comma t is the summation from j equals 0 to p of u bk comma j of t, then phi k comma j of x, like that. Here we see that u sub h is the numerical approximation. This is the numerical approximation which is given by this. Then p here is the degree of the polynomial we are working with. Then phi of k comma j, this phi of k comma j here is they are the local basis functions, which could actually be any functions at all, as we're going to see later. Then we have u sub k comma j, which are the local degrees of freedom. So you have local degrees of freedom, you have local basis functions, you have the degree of the polynomial. Putting all of this together, we can get the numerical approximation. So unlike continuous finite elements, the polynomial approximation on one element does not have to match the polynomial approximation on its neighboring element. So that's the idea, where the idea of discontinuity comes from. In the regular finite element methods that are continuous, the polynomial approximation on one element has to match the polynomial approximation on its neighboring elements. We're talking about finite elements that you can count or so. Now, we talk about the idea of discontinuities. Why do we allow discontinuities in discontinuous Galerkin? At first, allowing discontinuities may seem strange. if the physical solution is smooth, why deliberately introduce jumps there? So, because most of the times discontinuity is a problem in mathematics, right? So the answer is that discontinuity provides several important computational advantages. So injecting discontinuities can give us some mathematical advantages. For instance, we can have the idea of locality, where each element has its own independent degrees of freedom. So, we see the degrees of freedom here as represented by U sub k, comma j of t, which are local degrees of freedom. So, because of locality, right, like that, so each element has its own independent degrees of freedom. So number two, we can have higher order approximation. So we can use polynomials of degree 0, 1, 2, 3, and so on inside each element. So for each element, you can use different polynomials degrees. Then excellent treatment of transport. Now, discontinuous Galerkin methods are particularly effective for advection and hyperbolic conservation laws. So that's the idea of transportation there. Then you have conservation. Numerical fluxes can be designed so that the method is locally conservative. So you can have local conservations because there are discontinuities. So you can have pockets, every element, having its own unique behavior, its own unique conservation locally. Then we have parallel computation. Now, because of discontinuities, now elements can communicate primarily through boundaries. So you can now they can now be dealt with in parallel. Then you have mesh flexibility. Of course, the whole idea of finite element, right? It involves discretization, and then you have meshes and everything. So discontinuous Galerkin works naturally with complicated meshes and element shapes. Therefore, the discontinuity is not an error, it is an intentional part of the numerical formulation. So discontinuity here is not an error. We are intentional about it because it is an intentional part of the numerical formulation itself. Then let's go ahead to talk about continuous Galerkin versus discontinuous Galerkin. Now, in a standard continuous finite element method, neighboring elements share degrees of freedom. So in normal finite elements, neighboring elements will have to share the same degrees of freedom. So for instance, at an interface, x sub I plus 1, x sub I plus half. So we have the numerical estimation, right? Don't forget use of h here. We had that to be the numerical approximation. So for that numerical approximation at the negative side, so x negative sub I plus half, it is exactly the same thing as the numerical approximation u sub h at x positive. So when we talk about x negative and x positive, right, we are saying something like this. um Imagine that let's say you have a plot like this, just a plot like that, and then you have this point right here. So this point can be approached. Okay, let's project it to the line here. Okay, this point can actually be approached. It can be approached from the positive side, or it can be approached from the negative side. So normally in the continuous finite element, right? So this and this, the approach from the negative and positive side should be equal like that. So that's the idea for continuous finite element. But for discontinuous Galerkin now, that will not be the case. So in the discontinuous Galerkin, this condition is not imposed. So it is not necessary that at that interface, the value on the negative side should be equal to the value on the positive side. Instead, we can have the value on the negative side not being equal to the value on the positive side. And that is where the discontinuity comes in. So in general, we can have this for discontinuous Galerkin. Now, the two interface values are denoted by, so talking about the two interface values now. So U minus, from the negative side now. So UH minus, this expression can be summarized as U minus, and that is equal to the limit of UH of X. As X approaches X, I plus 1, I plus half from the negative side. That's u minus. And we have u plus. That is the limit of the numerical approximation as a function of x. As x approaches x, x sub I plus half from the positive side, which I showed just now. Then the difference between u minus and u plus is that it's given as this now. So we have this u equals u plus minus u minus. So that's the difference between them. And that is called the jump. So the jump is the difference between the values from the two interface values like that. So the difference between u plus and u minus is called the jump. And that is like that. So the discontinuous Galerkin therefore replaces strong continuity with weak communication through numerical fluxes. So because we have jumps like that. So let's talk about a model problem in terms of linear advection. Consider the one-dimensional advection equation, u sub t plus a u sub x equals 0. Of course, we know another way to write that is this. Another way to write u sub t plus is that a u sub x equals 0. That's the advection problem. Okay. Another way to write this, okay, u sub t plus a u sub x equals 0. So that's a neat way of writing that. We could as so it could also be written as partial u partial t plus a partial u partial x equals 0. So we have time. This is the time domain, and this is the space domain. So here we talk about time and space for partial differential equations like that. So in that case, where a is a constant velocity here. So a is a constant velocity. And then the equation describes the transport of quantity u with velocity a. So it can be this u now, it can be heat, it can even be flow or anything, but we know there's a transportation happening. So the equation describes the transport of a quantity u with velocity a. So if a is greater than 0, the solution moves to the right. Then if a is less than 0, the solution moves to the left. So we're talking about flow right now. So for a greater than 0, that's positive velocity. So we have the flow moving to the right. And if the solution moves to the right. If a is less than 0, the solution moves to the left. So for an initial condition, then we can then have u of x comma 0 equals u naught of x. So in this case, now that is the flow of heat or whatever we are considering at the initial time. So we have the space component, but the time component is 0. So at time 0, we have u naught of x. That's the state at the initial time. So the exact solution of this would then be u of x comma t equals u naught of x minus at. Now, in that case now, so it's more like we are solving this. We have u as a function of x comma t is that initial value into x minus at, like that. Of course, for something like this, we can use things like separation of variables like that. Now, for example, if u naught of x, now this u naught of x is sine 2 pi x, then we can say u x comma t. So because we now have u naught like this, so this is u naught of x minus at. So and u naught of x now is sine pi of x. So wherever we find x, we put x minus at. So we then have sine of 2 pi into x minus at, like that. Now, this simple PD is an excellent starting point for understanding the discontinuous Galerkin. So this simple PDE for advection u sub t plus a u sub x is an excellent starting point for understanding discontinuous Galerkin finite element. Now let's look at the characteristics of the advection equation. Now considering u sub t plus a u sub x equals 0, the characteristic curve satisfies the x dt equals a, and that's why we're able to get the result we got the other time. So we get the x dt equals a, and if we integrate that, so we have the x dt equals a, right? So the x dt is equal to a. So that means the x is equal to a dt. Now, if we integrate, we have integral of dx equals integral of a dt. That means we have integral of dx equals a is constant, so we have dt like this. So integral of dx is x, then we have a integral of dt, that's t. Then we need a constant like this. So at the end of the day, x is a t. Okay, we have, of course, that c there is an arbitrary constant. So at the end of the day, the constant c is x minus 80. So the constant t is x minus 80. So this simply means that c here is equal to x minus 80. So that's the arbitrary constant in that case. So as a result of that, we can have, okay, yeah. So we have that x minus 80 is c. So along a characteristic then, du dt will be zero. So therefore, the solution remains constant along the characteristic curves because du dt along a characteristic is zero. Then this gives the physical interpretation. The initial profile is transported without changing shape. So for the ideal linear advection equation, for a greater than zero, so information travels from left to right. Okay, so it travels to rightwards. So this directional flow of information will determine the appropriate numerical flux. So the initial profile is transported without changing shape, as we see from that. Now, let's talk about dividing the domain into elements. Let the computational domain, so the domain under which we are operating, let's say we have heat flowing in a bar, right? You have heat flowing in a rod, for instance, as we have for partial differential equations sometimes. Okay, this is not looking pretty. Let me see if I can redo that. Okay, so imagine we have a bar. So this is the initial point zero, and this is the final point L. So this is the whole of this is omega, the domain over which we are taking our expression, right? So this is omega like this. So the whole domain right now, we want to divide it up. So let the computational domain be omega, which is the closed interval 0 to L, like I showed on that iron bar. Divide it into n elements. So if you divide it into n elements, it means omega is the union of all I equals 1 to n of ki. So it means you have ki, that's k1 union k2 union k3 union k4 up to union kn. Okay, let me try to write that out. So now we are saying that omega is equal to uh all the unions. Okay. Okay. Union from k equals 1 to n of all the, let me say that again. Um yeah, okay, I equals 1. Okay. I equals 1. So we have, this is I equals 1. So I equals 1. I is equal to 1 up to n of all the ki's. That means we simply have k1 union k2 union k3 all the way down to union kn. So that's us dividing up all of these things now. So it's more like we divide up this. So you have k1, k2, k3, and we keep dividing like that all the way down until we get to kn like that. So the whole domain now is the union of all these components of that domain like that. So with that in place, then we have, so for a uniform mesh, we can then have ki is the closed interval of xi minus half all the way to xi plus half like this. So, and with element size, h is, so the element size is now h, which is the difference between xi plus half minus xi minus half. So for example, let L be equal to 1 and n is equal to 4. So that means we have 0 to 1, right? So if L is 1 and n is equal to 4, then we have h to be 1 over 4, 0.25. So all these small divisions we now did now will be from, so for K1, that will be from 0 to 0.25. So you keep incrementing by 0.25 because L is 1. So the whole length now is now, so we are now saying this is 0, this 0 here now is 0 to 1. So, and then each length of this one now is 1 over 4, because n is 4. So 1 over 4. So we have 1 over 4. So from here to here is 0.025 or so. 0.025, and then we keep going like that from one division to the other. So 0.25, right? So 0.25, 0.25 to 0.5. So, for this now we have 0, to 0.25. So so this is 0.25, this is 0.50, 0.75, 0. I mean 1.00, 1.25, and it keeps going just like that. So that shows us that K1, for instance, K1 is from 0 to 0.25. So this K1 now, K2 is from 0.25 to 0.50, and K3 is K3 is from 0.50 to 0.75, and it keeps going on like that. So, with all of that in place now, we have 0 to 0.25 for K1, K2 0.0, 0.25 to 0.5, K3 0.5 to 0.75. So K4, that's the last one now because we have four divisions. So K4 is now 0.75 to 1, like that. So that's a simple way to explain that. So the discrete Galerkin approximation space. So we then define the discontinuous finite element space V sub H super P, and that is equal to the collection of all V's such that V slash K is an element of P raised power P of K for every element K. So here P raised power P of K denotes the set of polynomials of degree at most P on element K. So we then have piecewise constant approximation. So for P equals 0 now, we have U sub H slash K equals UK. That's for P equals 0. Now, we then have piecewise linear approximation. For P equals 1, U sub H slash K is equal to U sub K, comma 0 plus U sub K, comma 1, X. And it keeps going like that. The piecewise quadratic approximation then, for P equals 2, we have U sub H slash K equals U sub K, comma 0 plus U sub K, comma 1X plus U sub K, comma 2X squared. So the important point is that every element has its own coefficients like that. So every element has its own coefficients. So we have a simple interface example here. Suppose two elements meet at x equals 0.5. Don't forget, for discontinuous Galerkin, we are saying that for a particular point, right, the value approaching it and the value from left and right, from negative and positive sides, are not the same because there's a jump at that particular point. So suppose two elements meet at x equals 0.5 and the left element gives 2.0, that's the negative side, gives 2.0, while the right element u plus gives 1.0. Then the numerical solution has a jump, which is u plus minus u minus, which we saw before, and that'll be 1 minus 2, which is minus 1. So there's a jump of minus 1. So in this case, there's no requirement that u minus should be equal to u plus because we are dealing with the discontinuous Galerkin finite element method. Instead, the discontinuous Galerkin method must determine how information crosses the interface. So we have to, that's what DG talks about. That is the role of the numerical flux. How does information cross the interface? Now, deriving the discontinuous Galerkin weak formulation. If you start with ut plus u sub t plus a u sub x equals 0, that's the advection equation we saw the other time. So let v be a test function. So v is a test function belonging to the discontinuous Galerkin finite element space. So if you multiply the PDE by v, so you then have ut multiplied by v plus a u sub t multiplied by v plus a u sub x multiplied by v. Of course, 0 multiplied by v is 0. So if you integrate over an element k, so you have integral of utv dx over k, then au sub x v dx over k, and all of that is equal to 0. So we now integrate the spatial derivative parts. So for the spatial derivative part, now we do integration by parts. So using integration by parts, now see this part. So this is the spatial part, this is the time part. So for the for this part now, we can easily just go straight. But for the spatial part now, we need to do integration by parts. So then we have integral over k of a u sub x v dx, and that will be equal to auv evaluated at dk minus integral of k auv of x dx. That's integration by parts right there. So so in that case, we then have therefore integral of k for u sub t v dx. So this is this first part now. So we have integral of u sub v u sub t v dx, this part now. So for this since this whole expression is now this whole thing, so that will now be integral of this integral here, negative. So we put this here. So instead of this now we put this whole thing. So we have u sub t v dx minus integral over k of auv of x dx plus this auv evaluated at the change in k, and all of that is equal to 0. So in this case now, this is weak. This is the weak formulation on a single element. So the important feature is the appearance of the boundary term. So the important feature is the appearance of the boundary term. So in discontinuous Galerkin, neighboring elements may have different values of u sub h at the same interface. So you have the same interface, but neighboring elements have different values. Therefore, we need a special treatment of the boundary flux like this. So for this part, now you may want to review the idea of integration by parts, where we say that, so here, clearly, so for integration by parts, right, this is what we do. So it's more like you have I equals integral of u dv, generally speaking. So for integral of u dv now, so you need to identify, so there are two parts here. So you can say so here you have so because of this u dv, we can refer, so we refer to the product rule, refer to product rule. So if you refer to the product rule, what do you have? You remember for product rule, if you actually have a function y equals uv, so dy dx overall will be this one, the v dx plus v du dx. That's product rule. So if you multiply through by dx, so you get dy equals u dv plus v du. So in that case, at the end of the day, what we are looking for y, right? So how do we get that y? So we integrate. So we integral of dy equals u integral of dv plus v integral of du, like that. So at the end of the day, we have this dy now is simply y, and then you have u. Okay, I'm trying to see if this is proper. I think it's better to just leave the whole thing alone the way it is. So we have integral of u dv plus integral of v du. So don't forget, the solution we need is integral of u dv, right? So, and we have that here. So y now is equal to integral of u dv plus integral of v du. Don't forget, the original y is actually uv here. So we have uv is equal to integral of u dv plus integral of v du. So we can now make this the expression, what we want. So it means that integral, okay, I guess I want to change now. So integral of u dv. So from here now, integral of u dv is equal to uv minus integral of v du. So it's more like transferring this here so we can get this alone. So that's uv. So if you apply that to that expression we have on that page. So if you apply that to this function now, this expression here, okay, so it's like we have, so x can go with dx like that. So we then have a u, this over x now. So auv over evaluated over decay minus the rest now, integral of like what we have here now, v du. So here now, our u is more like u sub x dx, and our v is v, no, u is u sub x. So that's why we can get this now. Then or even u sub x v, and then for the other part we have dx like that. So that's how we get that result, and then we fix that up here, and that we end up getting this final result here. Now, talking about the numerical flux now, if you have for a conservation law where u sub t plus f of u sub x is equal to 0, the physical flux is f of u. At an element interface, the discontinuous Galerkin introduces a numerical flux where f hat is equal to f hat of u minus comma u plus. So the discontinuous Galerkin weak formulation then becomes integral over k of u sub h sub t v dx minus integral over k of f of u sub h v sub x dx plus f cap of v evaluated at d change in k is equal to 0. So for linear advection, now we see that f of u now, the f of u is then au for linear advection. That's still referring to the original equation we started with. So this au here for linear advection. So, um, so in that case, we then have integral over k u sub h of t v dx minus integral over k of so f of uh now, so if f of u is au, f of uh now becomes au h vx v sub x dx plus this f cap here v evaluated over dk equals there. So what has changed is this f of which is now a multiplied by v sub x dx, like that. So the numerical flux is the mechanism through which neighboring elements can communicate. So that's the mechanism through which neighboring elements can communicate. Now let's talk about consistency of a numerical flux. A numerical flux should be consistent with the physical flux. Consistency means the f cap of u comma u should be f of u. So that's the consistency. So for linear advection, that means that f of u is equal to au, like this, and then therefore f cap of u comma u is actually au, like that. So this condition guarantees that when there's no discontinuity, we can say that the flux, the value from the left is equal to the value from the right, and that is equal to our u. So the numerical flux then reduces to the correct physical flux, which we see in the continuous sense of the finite element. So let's talk about central numerical flux. Central numerical flux. One simple choice is the central numerical flux. So f cap sub c, that's the central, is equal to half f of u minus plus f of u plus. Then for linear advection, it means that f cap f hat of c is equal to a over 2. We already know that f is au, right? So in this case, because of the half we now have, so it's more like we have half times a times u. So that's half times a, which is a over 2. And then our u now is u minus plus u plus, because we're dealing with the central thing. So the central part is the fact that so it's more like we have au, right? So that's a times half into u minus plus u half for the centralized stuff, like that. So or if you want to just break it down, actually, so it's more like we have, okay, if I snip this and bring it over, then I can easily just go with that. So let me snip this. So look at this expression here. We snip that, then I copy it. So copy it and take it to our page here. So if I paste this here now, so we can work with this. So this FC cap here, this F cap sub c is equal to half. So f of u minus is that because of the f we got already, we know that's au minus plus au plus, because f itself is au. So f of u minus will be au minus. So in this case now, we can factor out the a. So we have half multiplied by a multiplied by u minus plus u plus, like this. So that means we have a over 2 into u. Oh, where did I get the one from? Sorry. So this one should not be there. So we have au minus plus, I mean, uh, a over 2 into u minus into plus u plus. So that's the expression we have for the particular situation we are considering right now. So because we already agreed somewhere, for f of u, we already know it is au in this right here. So f of u is au. So with that, we take care of the central flux. So the central flux treats both sides numerically, symmetrically. So although it is simple and consistent, it may provide insufficient numerical dissipation for pure advection and can allow non-physical oscillation. This motivates the upwind flux. So that's central flux. So because of the problem of the central flux, then we have the upwind flux. So let's look at the upwind flux now. The upwind flux uses the state from which information is arriving. So for u sub t, the advection equation, u sub t plus a u sub x equals 0 with a greater than 0, we know information is going to flow. Information travels from left to right because a is greater than 0. Therefore, in that case now, because information is traveling from left to right, we then have f cap of u to be a u minus because information is flowing from left to right, because the left state is the upstream state now, because so information flows from higher point to lower point. So f cap of u is equal to a u minus because the left state is the upstream state. Now if a is less than 0, of course we know it's going to be f of u is going to be a u plus. So if a is less than 0, information travels from right to left. So as a result of that, the right state is the upstream state. So information flows from the positive side to the negative. So f cap of u will be au plus here. So in general, we see that f cap of u will be a. Of course, we already know f is au. So overall, in the case of the upwind numerical flux, we have f cap of u equals a. Then the step function u minus when a is greater than 0, u plus when a is less than 0, which is the corresponding upstreams for the different values of a. Now let's take an example of numerical flux. Suppose a is 2, u is minus 3, and u plus is 1. So the central flux will simply be f cap of c, which is a over 2. A is 2, so we have 2 over 2 into u minus is 3, u plus is 1. So 2 over 2 into 4. So that's simply 4. Then for the upwind flux, we have for a greater than 0, we have f cap of u. That's 2 times 3, which is 6. That's f, that's uh, a u minus. That's 2 times 3 is 6. Therefore, fc cap is equal to 4 and fu cap is equal to 6. So the difference occurs because the upwind recognizes the information is entering the interface from the left. So information enters the interface from the left. That's for a greater than 0 for the upwind flux. Now, for the so we then talk about Lax-Friedrichs numerical flux. Another important flux is the Lax-Friedrichs flux. So in that case now we have f cap lf, which is half f of u minus plus f of u plus minus a alpha over 2 into u plus minus u minus. Don't forget f of u minus will be is au minus, f of u plus is au plus. So where alpha is an estimate of the maximum wave speed. So for linear advection, alpha is the absolute value of a. All right, so thus we can say that f cap linear Lax-Friedrichs will be, of course, from here we know this is au minus, this is au plus, so a can be factored out. So we have a over 2 into u minus plus u plus minus. So this alpha now is absolute value of a all over 2 into u plus into minus u minus. And of course, in this case now, this is actually the jump. That's the that expression you represent as this now, as this u, which is u plus minus u minus, like that. So that's actually what is known as the jump, like that. So we have that. So when a is greater than 0, so when a is greater than 0, we then have when this a is greater than 0, so we have for a greater than 0, right? We have, this will be this as good as we have the two together. So in that case, we can have the negatives, this will be minus this now. So the plus side will go out. So we just only have a over 2 u minus plus minus a over 2u minus. So we then end up having half au minus plus half au minus, which will end up giving us au minus, because a is greater than 0 now. So this is guaranteed a over 2, like that. So therefore, for consistent positive linear advection, the Lax-Friedrichs flux coincides with the upwind flux. So I remember the upwind flux we had before is actually the same thing as this for a greater than 0. So we have au minus, like this. So we can actually so we can set up a Python code for this flux comparison in Python. So you have the central flux, u left, u right, a. So you return 0.5 times a times u left plus u right. Exactly the same thing we did with the equations. Then for the upwind flux, you have u left, u right with a. If a is greater than 0, return a u left. If else, return AU right, that is A less than 0, then for the Lax-Friedrichs flux, so we just have the absolute of A there and you define all of this. So if U left is 3 and U right is 1, just like we've been doing, and A is 2.0, we end up getting this result now. So central flux is 4, upwind flux is 6, and Lax-Friedrichs is 6, because upwind flux and central flux are pretty much the same thing, like that. So we then go on to talk about the reference element. Okay, so we see the central flux, upwind flux, everything we've got before, exactly 4, 6, and then we see Lax-Friedrichs numerical flux is the same thing as the upwind flux, like that. So let's talk about the reference element now. So to identify the finite element calculations, map every physical element to the reference element. So where psi lies between -1 and 1. In fact, psi takes value from -1 to 1 in short. So for physical element, k now is the absolute value. I mean the the interval, the closed interval xl to xr, and then we define x of psi to be xl plus xr over 2 plus xr minus xl over 2 multiplied by psi. So if you then define the Jacobian on that now, so j, we can then say j is xr minus xl over 2 of psi, like this. So that's more like dx psi d psi. So this will go and this will remain. So then we can say that x is now xc. So we can then say x is xc plus j epsilon, I mean j psi. So x is equal to xc plus j psi, and where xc, so xc is now this expression divided by 2. So this is our xc here. All right. So uh, the differential transforms according to dx equals jd the psi. Okay. So we have the x d psi is basically this expression. So and then that's why we have our j here. So this expression, when we differentiate this, we get this. So dx is equal to j d psi. Now, if you derivative transformation now, so because x is equal to x plus j psi, we can then have dx d psi to be j. So dx d psi, of course, here is j, clearly. And therefore, we can have, so if dx d psi is equal to j, what does that mean? So dx d psi is equal to j. So we now need d dx. Dx d psi is equal to j. So we need d dx. Okay. So dx d psi, psi can be such a problem, is equal to j. So that means that dx is equal to j d psi. So then if we need d dx here, so it means we have d dx equals d j d psi. And since j is like a constant, so to speak, we can then have d dx is equal to 1 over j, 1 over j d d psi, like this. So that's this expression here, which we have on the in the notes. So d d psi is 1 over j, d dx is 1 over j d d psi. So the transformation allows us to construct basis functions and element matrices on the same reference element. So for a uniform mesh now, the reference element calculations can be reused for every physical element. So then we talk about the piecewise linear discontinuous Galerkin basis. For a simple discontinuous Galerkin implementation, choose polynomial degree p equals 1. So if you then use the reference basis, phi of phi phi naught of psi equals 1, and then phi 1 of psi equals psi, then the local approximation becomes u of h psi of psi, u sub h of psi comma t is u naught of t, then phi naught of psi that we have here, plus u1 of t plus phi 1 of psi that we have here. Therefore, u sub h of psi comma t is equal to u naught of t, psi of the theta of psi, that's simply 1 here. So we just have u naught of t. Then on this other hand, you have u1 of t, phi 1 of psi, that's simply psi. So the coefficients u naught and u1 belong only to the current element. So because we are dealing with the current time here, so interface values from the polynomial, then for u sub h of psi, which is u naught plus u1 of psi. So the left endpoint corresponds with psi equals -1, like that. So therefore, UH of -1 will simply be u naught minus u1, u naught minus u1. So the right endpoint corresponds to psi equals 1. So that's the right endpoint corresponds to psi equals 1. Therefore, UH of 1 is u naught plus u1, like that. So, it's more like you put -1 here. Don't forget, we said psi takes values from -1 to 1. So for the left endpoint, right? In case you've forgotten, we said -1 is less than or equal to psi, and that's less than or equal to 1. So this is the endpoint, left endpoint, and this is the right endpoint. Right endpoint, left endpoint, like that. So if psi takes -1, so we can have u sub h of -1 to be something. Then if psi takes this, we can have u sub h of 1. So, and when we do that substitution, that's why we end up getting what we got there. If you substitute that into the expression we have on that page. Okay, so if you come here now, so for psi equals -1, so it means that you have u naught plus u1 times -1. So u1 times -1 is minus u1. So that's why u of -1 is u naught minus u1. So the right endpoint, which is psi equals 1 now, so uh of 1 is u naught plus 1, because this is 1 now. u1 times 1 is 1. So in that case now, you can then have u sub l is actually u naught minus u1 altogether. And then u sub r. So for the left, you have u naught minus u1. For the right, you have u naught plus u1. So these traces are used to calculate the numerical fluxes at the element boundaries. So we then have element mass matrix. So the mass matrix is defined by m sub ij, which is equal to integral over k of phi1 phi j dx. And using the fact that dx is j d psi, so we obtain that we have m sub ij equals j, which is constant, take it out. Then you have integral from -1 to 1 of psi1 of psi, f, yeah, phi1 of psi, phi sub 1 of psi, phi sub j of psi d psi. So j is out already. So in that case, if you then take phi not to be 1, so we had a case before where we had the values of phi. So phi naught of psi is 1, phi 1 of psi is psi. So if that is the case, then we then have phi naught is 1. That's phi naught of psi is 1, and phi 1 of psi is actually psi, the psi. So in that case, we can obtain m to be j into, so if you break all this up, you then have integral from -1 to 1 of 1 d psi, then integral from -1 to 1 of psi d psi. Then on the other side, you then have integral from -1 to 1 of psi d psi. And then so you just keep going, one psi, then one side, then this will be another side. So we're talking about like some kind of Jacobian, and then you have psi squared, like that. So in this case now, if you integrate one d psi, so it's more like you have psi to be evaluated from -1 to 1. So so maybe I'll do, let me do so here you see, I think this is the most important part here now. So you have theta naught, you have psi minus 1, psi from -1 to 1 of 1 d psi. So this one now, then this psi one, this other one, you have psi -1 to 1 of this psi. So that's, when you put 0 here, you put 1 here, and you put so this and this will be the same. And then here, if you put 2, you get psi squared. So if you integrate the psi, so let me just do only that one, and then I'll just use that to explain the rest. So imagine that you have the integral from -1 to 1 of 1 d psi. So that means you have integral from -1 to 1 of d psi. And if you integrate d psi, you simply get psi, right? From -1 to 1. So put all of that together. So put the top value, you have 1, minus, put the lower one, you have -1. So that means you have 1 plus 1. That means that integral integral from -1 to 1 of 1 dψ is equal to 2, like this. And so you can then you just integrate all the other ones following that too. So coming back here now, you then have you have integral of psi dψ. Of course, for psi, this is psi squared. So that's half into psi. So for half into psi now, that's half. So if you integrate this, that's psi squared over 2. So you have half into psi squared. So if you put 1 squared, that is 1 minus 1 squared. That is also 1. Okay, I guess I need to do that for clarity's sake. So again, we are at this. You have integral from -1 to 1 of psi dψ. So that means you have so let's just integrate straight. If you integrate psi, you get psi squared over 2, and that's from -1 to 1. So I like to put out the constant. That's half into psi squared from -1 to 1. So that means you then have half into, so put 1, that's for psi squared, put 1, so you have 1 squared minus, put -1, that's -1 squared, like that. So you then have half into 1 squared is 1, minus 1 squared is also 1, because -1 times -1 is 1. So you have half into 0, and everything goes to 0. That means that integral from -1 to 1 of psi dψ is equal to 0. And that's why we have that other value there. So that's why this is equal to 0, this one right here. Therefore, psi squared dψ, that's 2 over 3. So in that case now you have 2, 0, 0, because this side, what you have here is also what you have here. So this is 2, 0, and then 2 over 3, like that. So that is what we call the element mass matrix. Then we talk about the element advection matrix. So the special term involves the special terms for this other one now. Okay, now the special term involves minus integral over k of a u h v x dx. So if you define Sij to be integral over k of phi I, then the phi j dx, like that. So it's as good as saying dx cancels dx, like that. And then you have phi I d phi j. So if you use d dx, so we already know d dx. If you use d dx to be 1 over j d d psi, so that means that dx itself is j d psi. So this dx can be j d psi. So what does that now mean? So we have s of ij equals integral from -1 to 1 of phi I, then the phi j d psi, because now dx has now been taken to be j d psi. So we have j d psi, and then dx again is j d psi. So the j will cancel themselves out, like that, because dx is j d psi. So we have j d psi, j d psi, j d psi, like that. So it's as good as they can cancel themselves out, but we just leave it like that. So you can notice that the Jacobian then cancels. So for theta, for phi of 0, you have 1. Then for phi 1, you have psi. Then we then have the phi naught the psi. That'll be 0. If you differentiate this, you get 0. If you differentiate this, you get 1. So as a result of that now, we simply just have, therefore, we then just have 0, 2, 0, 0, like that. 0 to 0, 0 in that case for the S sub ij. All right, so in this case now, we then go on to talk about semi-discrete DG system. So for each element, the DG formulation can be expressed as m du dt minus asu plus phi of 1 f cap of r minus phi of -1 f l cap equals 0. Therefore, m du dt, of course, so m du dt now will be, so we can transfer it to the other side. That'll be asu minus this plus this now. So, and if you multiply by m inverse, so du dt multiply by m inverse. So m inverse will cancel this out. So we have m inverse multiplied by this whole thing. So the PD has now been converted into a system of ordinary differential equations. So we already know m as we have here. So m has been obtained from here. And then even s, This S, we have it here. Then phi of 1, we can evaluate. Phi of minus 1, we can evaluate, depending on the expression of that phi is. So if you multiply, okay, so we have all of this. So the PD has now been converted into a system of ordinary differential equations. Then we have methods of lines now. So since we have a system of ordinary differential equations now, we can then use the method of lines. So after discretizing space, the PDE becomes an ODE system, du dt equals R of u. So that's the kind of thing we have here. So this is called the method of lines. So the overall process is this. You have the PDE, use spatial discontinuous Galerkin discretization. You get an ODE system, and then you can do time integration. Because for an ODE system, you have just one dimension. You have only time. For PDE, you have time and space, x and t and x. But now that you have converted to an ODE, you have only time. So we can then use standard ODE methods such as forward Euler, Runge-Kutta methods, SSP Runge-Kutta methods, implicit methods, or IMEX methods like that. So then we have CFL stability restriction. Explicit discrete continuous Galerkin methods require a sufficiently small time step. So a typical CFL restriction has the form, change in T is approximately less than C h over 2p plus 1 multiplied by the absolute value of a, where c is the CFL number, h is the element size, p is the polynomial degree, a is the wave speed here. So this shows that the time step decreases when the mesh becomes finer, the polynomial degree increases, and the wave speed also increases because c as c increases, the time step increases. As h increases, the time step increases. But p and a will make it reduce. So this shows that the time step decreases when the mesh becomes smaller. So as this becomes smaller, this becomes smaller. The polynomial degree p increases. So as this becomes bigger, this becomes smaller. And then the wave speed a, as this becomes bigger, this becomes smaller, like that. So a practice implementation must therefore choose change in T carefully. So we have a setup for that. Imagine this Python setup. So we need NumPy for numerical computations, and we need matplotlib to visualize. So the domain is L. Let's say the length of the rod is from 0 to 1. So we have one number of elements. So we want to divide from 0 to L. We want to divide it into 40 elements. And then we have the polynomial of degree 1. The advection velocity is also 1. So in that case, now H will simply, the time step, the element size will simply be L over N, 1 over 40. And the Jacobian of the mapping will be H, this H over 2 now. So if you run this, so we have element size is 0.025 because now it's 1 over 40 for each element. Then Jacobian is 0.0125 because we divide this by 2. So once we do that, then we can also construct the local matrices. So from what we did the other time, so from the mass matrix now we have 2.00, then 2 over 3. Let's say that's the value we have. Let's see, does it correspond with what we got initially? Okay, yeah. So this is exactly what we are declaring there. This 2002 over 3. That's exactly what we have right here. So with that in place now, we have the inverse of the mass matrix. So that's matrix inverse. We do the inverse of M using the linear algorithm, linear algebra function library from the inverse function from the linear algebra library from NumPy. So to find the inverse of M, and then we then reference the advection matrix. The advection matrix now gave us 0, 2, 0, 0 from what we got from S. Then we have basis evaluated at left and right points. So phi left, we have 1, 0, minus 1. Phi right, we have 1, 0, 1, 0, like that. So we then have the mass matrix, inverse mass matrix, and the advection matrix like that based on all these things. So we have so mass matrix now is 0.0250, 0.83, and the inverse of that will be is 40, 0, 0, 120. Then the advection matrix is now 0, 2, 2, 0. Then that leads us to the element centers. So to get the element centers now, we have xc to be we arrange all n plus 0.5 multiplied by h, like that. So if we plot all of that, we get the location. So the element center, you see it's perfectly at location 0, like this all the way through. So that's the center of everything we have. So we have the discontinuous Galerkin element centers as perfectly aligned at 3, for all values of x. Then we can talk about the initial condition. We allocate dg, we allocate dg degrees of freedom. So we have u now to be np0s n comma 2. So, and the initial condition now is at time t for all values of x now, because x is known. For all values of x at initial time, we have sine 2 pi xc, whatever xc is, the initial set slope coefficient to 0. So we have at time 1 now we have the slope at 0 0.0. So we can also run this to register that. Then we have 1.14. Why the initial condition is only an approximation. So the DG approximation on each element is UH of psi, which is U naught plus U1 psi, which we did before. So if you set U naught to be U naught of XC and U1 to be 0, so this will be gone, and then we only have U naught of XC now. So we then have so this and this approximates the initial function using only the element center value, because all the element center is 0 now. So a more accurate project approach is to perform an L squared projection. So the L squared projection 6 coefficients such as integral over k of UH minus U naught of v dx, because we had u sub x v dx now. So now we have minus u naught of v dx equals 0 for every basis stroke text function v. So for higher order DG simulations, accurate initialization through projection is that important. So we can have a code for that here. So DG special residual, we define the function for the right hand side u. So the u dt is all, so we initialize zeros like u. So for I in range n, so whatever n is, we have the left 1 minus I minus 1 divided by n. So this gives us the modulo division, whatever remains after we divide by n. Then for the right, we have I plus 1 modulo n. So then current, the idea of modulo is simply this, that if you have 5 modulo 2, that means when you divide 5 by 2, you get 2. What is remaining? 1. So let's imagine you have 10 modulo 3. Okay, that's also going to give 1. Okay, well, this is 1 because 10 goes in three times, the remainder 1. So the remainder is what you have left. Let's say you have modulo 20 modulo 4 is 0 because 4 goes in 25 times and nothing is remaining. That's what you have left here. So if you have 20 modulo 7, for instance, 7 goes in 22 times. That's 14 and the remainder is 6. That's the idea of modulo. So to get the leftover. So then we have all of that. Then you have current element traces. For the left current, now you have UI0 minus UI1. For the right current, you have UI0 plus UI plus 1. So then you have the neighbor traces also, like this. And then upwind flux, which we defined before, that's AU, like that. Then volume contribution, you have AS multiplied by U at any point I. Then you have the boundary contribution. So you have that boundary contribution here, and then you have the local residual, and then you run that, and that is stored up. So because it's going to return du dt, which you already defined up here. Now, understanding the DG residuals, the discontinuous Galerkin residual. So the residual contains two fundamental pieces. So you have volume contribution, which is ASU. So this describes how the polynomial evolves inside an element. Then you have the boundary contribution minus phi 1 FR cap plus phi minus 1 FL cap. This describes communication with neighboring elements. So thus, the discontinuous Galerkin residual is equal to volume physics plus interface fluxes. This decomposition is fundamental to understanding the continuous Galerkin implementations. Then we have RK4 time integration. So here now you define Runge-Kutta step 4. uh I think I need to save and reload this. I hope that works. So you define Runge-Kutta step 4 at UDT. So K1 you define that, K2 the whole Runge-Kutta thing. So we run that. That's the standard definition for Runge-Kutta. Then to run the simulation now, you have T equals 1.0, and then you have dt, the time step is CFL times H over 2p plus 1 absolute 8. That's the function that we defined before, and then we use the whole Runge-Kutta thing. This is coming up again. I hope it comes up pretty soon as we reload. Okay, all right. Okay, it's coming back up. So we're on this Runge-Kutta stuff, right? So um, we run this again. I guess since it has been reloaded, I have to rerun everything from the beginning to be sure all the codes are intact. Okay, so we set up the Runge-Kutta, then we run the simulation. So when you run the simulation, we get the time step one, and then the time we get the final time step, which is 1.0, and then the overall time step is 0.00833. And then we reconstruct the DG solution, the discontinuous Galerkin solution. We have xi is the length space for minus 1 to 1. We divide it to 20. We have the x plot and the u plot. So for I in range n, we map reference coordinate to physical coordinate. So x element is xc1 plus jxi. So you remember that xc plus j psi. Then reconstruct local polynomial. So u element, that's u I comma 0 plus ui comma 1 plus xi. I've been multiplied by xi. So you have all of these things. And then you plot the solution now. So to plot the solution, you have something like this. So you can see it has sharp edges, and that's why it is discontinuous. That's the discontinuous Galerkin solution right now in blue lines. So these are x values here from 0 to 1, and then the u values, it has very fine, very tiny values, 0.0 something like that. So we can compare with the exact solution. So to compare with the exact solution now, so you have the exact solution, that's 2 pi x plus minus 80. That's the original solution we had, right? So that's 2 pi x minus 80. Then you plot the figures for the exact and for the Galerkin, discontinuous Galerkin. So you can see u is the exact solution is this periodic stuff, but then the DG solution is just all at zero, talking about the centers. Then let's talk about periodic boundary conditions here. So for a periodic problem, u of 0 comma t is equal to u of L comma t. So the first element communicates with the last element, as you can see. So the first element communicates with the last element because they are equal. So the first element communicates. In Python, periodic indexing can be implemented using this. So the left, you have 1 minus I modulo n, then right 1 plus I modulo n. So for the first element, I is equal to 0, and then we obtain I minus 1 modulo n, which ends up giving us my n minus 1. So thus the last element becomes the left neighbor of the first element for sure. So this is a convenient way to implement periodic discontinuous Galerkin boundaries. Then we talk about conservation in discontinuous Galerkin. So consider the conservation law u sub t plus f of u sub x equals 0. Choose the test function, say v equals 1, and since v sub x is equal to 0, if you differentiate this with respect to x, we just get 0. So the volume derivative disappears. So we then have the element equation becomes d dt of integral over k of u sub h dx plus fr cap minus fl cap equals 0. Therefore, rate of change of element mass is equal to inflow minus outflow. So this is the discrete form of conservation now, because inflow is equal minus outflow gives us the rate of change. So we then have conservation across an interface. So suppose two neighboring elements share an interface. So for the left element, the interface contributes plus f cap. For the right element, the same interface contributes minus f cap. So adding two equations gives plus f cap minus f cap equals 0. Therefore, the internal flux cancels. So this is why, so the whole thing cancels right there. So this is why the same numerical flux must be used consistently by both neighboring elements. So the interface transfers information but does not create or destroy the conserved quantity. Then we have this discontinuous Galerkin and finite volume methods. So we said discontinuous Galerkin initially, we said it involves finite element, finite volume, and all of that. So there's a deep connection between discontinuous Galerkin and finite volume methods. If, for instance, p is equal to 0, that's polynomial degree, then the approximation is constant within each element. U sub h slash k equals u sub k. There's only one degree of freedom per element. So the resulting method resembles a finite volume method. Therefore, p equals 0 implies finite element like discontinuous Galerkin. So increasing p introduces higher order polynomial information within each element. So this gives the conceptual progression, finite volume leading to low order discontinuous Galerkin, which now leads to higher order discontinuous Galerkin. Then we have H refinement. So one way to improve accuracy is to reduce the element size. So H goes to H over 2. Then the mesh becomes finer. So if you reduce the element size, divide it by 2. So for example, N20 becomes N40 and N80 like that. This is called H refinement. So we are refining the element size. So the polynomial degree remains fixed while the number of elements increases. Then we can also have the P refinement, that's the polynomial size refinement. So another strategy is to increase the polynomial degree. For example, P equals 0 becomes P equals 1, P equals 2, P equals 3. This is called the P refinement. The mesh may remain unchanged, but each element receives a richer polynomial approximation. So discontinuous Galerkin is particularly attractive because it naturally supports both H refinements and P refinements. So we can refine the mesh, the element size, and we can refine the polynomial degree. So for instance, imagine this polynomial representation. Consider u of x is x squared. So on k 0 to 1, that's the domain over which we are doing all the work. So the reference mapping then can be x equals half plus half psi. So therefore, u of psi, because this is x now, u of psi is half plus half psi all squared. So it means that u of psi overall is u of psi overall. If you expand this now, that's half squared, you have 1 over 4. Then half times half psi, that's 1 over 4 times raised to power 2. This is half, so half squared, right? Then 2 times all of this. Okay, 2 times, this is half times half psi, multiplied by 2. That is 1 over 2 psi. Then half psi squared, that's 1 over 4 psi squared. So a degree 1 discontinuous Galerkin approximation cannot represent the psi squared term exactly. So therefore, if we need to use degree, so p equals 1 cannot represent this function exactly because it's already of degree 2. However, a polynomial of degree 2 can represent it exactly, so we can go for that. So now we also have the legend polynomial basis. So, the basis function we define in the original expression, it can be anything, right? So legend polynomials are widely used in high order discontinuous Galerkin method. So the first few are P naught of psi is 1, P1 of psi is psi. If you check my playlist on special functions, you'll see me. I talked about legend in some depth, and then P2 of psi is half 3 psi squared minus 1. So they satisfy the orthogonality relation where you have integral from -1 to 1 of Pm of psi multiplied by Pn of psi d psi equals 0, where m is not equal to n. So this orthogonality can simplify the mass matrix and improve the numerical structure of high order discontinuous Galerkin implementations. And then we have a simple Python code representing legend polynomial here. So this is what the whole code looks like. Okay, so we then have the legend basis function. You have the legend basis function like this. So this is what it looks like. I dealt with that very well under the special functions playlist. So P naught is this line at 1. P1 is you have this diagonal line, connecting from -1 to 1 like that. And then P2, you have a parabola like this, resting on minus 0.50. Then we have the Gaussian quadrature. So for the Gaussian quadrature, the discontinuous Galerkin requires integrals such as integral from -1 to 1 of phi I of psi, phi j of psi d psi. This can be evaluated using Gaussian quadrature. So integral from -1 to 1. I think I talked about Gaussian quadrature also, or some kind of quadrature, adaptive quadrature, I think, under numerical analysis. So, and that's approximately summation from q equals 1 to n sub q of w sub q g of epsilon x psi sub q. So here, psi sub q are quadrature points and w sub q are quadrature widths. So n sub q is the number of quadrature points. So you then have Gaussian quadrature is particularly effective because polynomial integrals can often be evaluated exactly with a relatively small number of points. So the Gaussian quadrature thing now, if you do a Python code for it, so from numpy.polynomial.legend, you can import Gaussian quadrature in short. So if nq is 5 and xiqw can be expressed from this. So you can get the quadrature points, xiq, and then the quadrature widths. So if you run this now, you get the quadrature point minus 0.90, minus 0.50, 0.53, because nq is 5 now, you have 1, 2, 3, 4, 5. Then the quadrature widths attached will be 1, 2, 3, 4, 5. Also those 5 values. So we can get the Gaussian quadrature like that. So all you just need are the points, like, so the value of q, so your nq, how many, so the number of quadrature points you want. So you define that, and then you can then get every other thing you need to get. So you can then get the quadrature points and the quadrature widths like that. Then talking about numerical mass matrix, which we talked about this before. So still based on this same quadrature. So define mass matrix with basis, and then you have J, and then NQ is 5. So, and this expression, that the one we obtain from this other point. So the XIQ and the points and the widths like this, then the length is based on the number of bases now, and then you have your matrix, so you can run this now and you get that. So M is returned there for you. So you may also want to visualize that M. So in that case now, if I just, so in that case I have to do this now. So I get, so the you can see the M has been printed at like this, 0.025. So same thing we saw before. Then we then have the discontinuous Galerkin for nonlinear conservation laws. So the DG framework also applies to nonlinear equations. So consider Burger's equations. So you have u sub t plus u squared over 2 sub x equals 0. So the non-linear flux is f of u, which is u squared over 2. Then the DG weak formulation is then this expression, integral over k of u sub t v dx minus integral over k u sub h squared over 2 vx dx plus f bar f cap v decay equals 0. So the major difference from linear advection is that flux now depends non-linearly on the function, on the solution. Then we have the Lax-Friedrichs flux for Burger's equation. So for Burger's equation, f of u is u squared over 2. So the Lax-Friedrichs flux then is f cap, which is half into f u minus f u plus minus alpha over 2u plus minus u minus. We saw this kind of thing before, where alpha is the maximum value of the absolute value of u minus and u plus. So this flux introduces stabilization based on the largest local characteristic, speed. Then we have the Burger's equation proper now. So u minus is 2, u plus is 1. So the physical fluxes are f of u minus, that's 2 squared over 2, which is 2. Then f of u plus, that's 1 squared over 2, which is 0.5. So the maximum wave speed is alpha, which is maximum of 2 or 1, which is 2. Therefore, f cap is now half into 2 plus 0.5 minus 2 over 2, 1 minus 2. So putting all the whole thing together, you have 1 over 2.5. That's 2. So this is 2 plus 0.5. That's 2.5 over 2. That's 1.25. Then this is 1 minus 2. That is 1, right? So 2 cancels 2. So that's plus 1. So you have 2.25. So in this case now, the for the flux will be F cap, which is 2.25. So that leads us to the discontinuous Galerkin for diffusion. So DG is also applicable to elliptic and diffusion equations. So consider Poisson's equation minus grad squared u equals f. So in continuous finite element, neighboring elements are usually coupled through continuity of the approximation. So in DG, the solution may remain discontinuous. So this requires interface terms involving jumps and averages. So important DG diffusion methods include symmetric interior point penalty Galerkin SIPG, non-symmetric interior point Galerkin, incomplete interior penalty Galerkin. Symmetric interior penalty Galerkin SIPG, non-symmetric interior penalty Galerkin, and incomplete interior penalty Galerkin. So the central idea is to weakly enforce the appropriate interface behavior. So it's all about interfaces, like we've been seeing all along. So jump and average operators now. So for an interface, we define the jump. U is u plus minus u minus. We started with that initially. Define the average. The average of that is half u minus plus u plus. For example, if u minus is 3, u plus is 5, then the jump is 5 minus 3, which is 2, and then the average is 3 plus 5 over 2, which is 4. So the jump measures discontinuity, while the average provides a representative interface value. So this is an interface value, while this is a discontinuity, which the jump represents. So it's jump and average operators. Then we have interior penalty stabilization. So a typical interior penalty formulation contains a term of the form sigma over h, then jump u and jump v, where sigma is the penalty parameter, h is the characteristic element size, this is the solution jump, and v is the test function jump. So the penalty discourages excessive large discontinuities, while if the penalty is too small, the stability can be lost, and if the penalty is unnecessarily large, the resulting system can become poorly conditioned. Thus, the penalty parameter must be chosen carefully. Then we have the discontinuous Galerkin metric structure. So after spatial discretization, many DG problems can be written as m du dt plus au equals f. Here, m is the mass matrix, a contains volume and interface contributions, f is the forcing vector here. So normally, if this was equal to 0, that would have been what we call uh homogeneous. But now if you have a forcing vector like this, it becomes non-homogeneous. So because discontinuous Galerkin basis functions are local, the mass matrix has a block diagonal structure like this. So this locality is one of the major computational advantages of discontinuous Galerkin. That's the matrix structure right there. So then we have the locality and parallel computing now. So I mean, one of the advantages of discontinuous Galerkin is the fact that we can have parallel computing because each element can be in its own locality. So each discontinuous Galerkin element has its own degrees of freedom. So for a one-dimensional mesh, an element primarily communicates with its neighbor. So K1 only can communicate with Ki minus 1 and then Ki plus 1. So these elements can therefore perform most of its calculations independently, and that's the idea of parallel computing there. So this makes discontinuous Galerkin particularly attractive for parallel computing. So the basic computational pattern is you have local volume computation plus local phase communication. So this structure maps naturally onto modern parallel architecture. So you see some computing coming into this. So then talking about stability. So for stability, we have a numerical method should prevent numerical errors from going without control. That is the idea of stability. So for linear advection, consider the discrete energy E of t, which is 1 over 2 integral over the domain. Then you have UH squared dx. So for suitable DG formulations, numerical fluxes and boundary conditions can produce an energy estimate of the form dE dt less than or equal to 0, or an appropriate boundary controlled version. This means the numerical method does not generate unlimited artificial energy. So because there's a boundedness on that, a boundary on that. So the choice of numerical flux is therefore closely connected to stability. So if there's no boundary, then there's no stability. That's basically the idea here. That's why the EDT is less than or equal to 0. And then we have numerical dissipation. Upwind type fluxes introduce numerical dissipation. We calculated the whole thing before. So all pointer fluxes introduce numerical dissipation. This can be beneficial because it suppresses non-physical oscillations. However, excessive dissipation can smear important physical structures. So there's a fundamental numerical trade-off. You have stability versus numerical dissipation. So a discontinuous Galerkin method seeks sufficient stabilization without unnecessarily destroying accuracy. So we have stability and numerical dissipation right there. Then we have smooth solutions versus shocks. So high order discontinuous Galerkin methods work extremely well for smooth solutions. However, nonlinear hyperbolic equations can develop discontinuities such as blocks. So depending on the problem you end up solving, right? So you can have some behaviors like that. So high order polynomial approximations near a discontinuity can exhibit oscillations related to the Gibbs phenomenon. Therefore, practical high order discontinuous Galerkin solvers may use slope limiters, modal filters, artificial viscosity, troubled cell indicators, shock capturing methods, and the basic principle is this: high order in smooth regions and additional stabilization near discontinuities. So as a result, so to avoid all these troubles, right? So you need high order in smooth regions and additional stabilization near discontinuities. Then we have the boundary conditions in discontinuous Galerkin. So boundary conditions are incorporated through numerical fluxes. So for u sub t plus a u sub x equals 0 with a greater than 0, information enters the domain through the left boundary. Therefore, the left boundary requires an inflow condition. So for example, u sub 0 comma t equals g of t. At the right boundary, information leaves the domain like that. So the distinction between inflow and outflow is fundamental for hyperbolic discontinuous Galerkin methods. So we have a simple code here. So periodic boundary conditions in Python. So don't forget, we are coming, all the codes we have written before now should come together. So this one cannot operate without them. So if you define a function called periodic neighbors for in. So for the left, you have I minus 1 modulo n. Then for the right, you have I plus 1 modulo n. So this gives, if you have I minus 1 and you divide by n, whatever is remaining is the value of left, and the right, we also have that. So then you return left and right. So for I in the range n, so left and right, right is equal to periodic neighbors I comma n. So if I is less than 3, you print element I, then left is left, right is right. So for element 0 now, left is 39 and right is 1. Then for element 1, left is 0 and right is 2. For element 2, left is 1 and right is 3, depending on, based on what we are dealing with here. Don't forget we have defined n before now. So the measuring numerical error now. Suppose U is the exact solution and U sub H is the discontinuous Galerkin approximation. So of course, error measurement is where we want to know how we want to make sure everything we are doing is within an acceptable error limit. So a common measure is the L squared error. So you have the norm of U minus UH L squared, that's num2, is equal to integral over omega of the absolute value of u minus UH squared dx, all raised to power half. So for smooth solutions, DG can achieve high order convergence. So a typical asymptotic relationship is the norm of u minus UH L squared approaching CHR. So where R is the observed convergence rate now. So that's us measuring error right there. Then estimating the convergence rate. So suppose E sub H is approximately CHR. So taking logarithms gives log EH equals log C plus R log H, like that. C times H raised to power R. So therefore R now is log E sub H sub 2 all over E sub H sub 1. Then then everything over log H sub 2 slash H sub 1. If the mesh is refined from H1 to H2, that's what we have there. So we can estimate the convergence rate from the corresponding numerical errors. So, and this is us doing that. So imagine for Python convergence calculation for this now. So we have, you import, okay, I think I can make this big. So import number as NP. So age values, you have an array, 1 over 20, 1 over 40, 1 over 80, 1 over 160. So this is you refining the mesh, the element sizes, and then the errors now. You have the errors associated with each one, 2, 3, 4. So you also have 4 errors, 2.0 e raised power minus 3, 5.0 e raised power minus 4, then 1.25. That's 1.5 times 10 raised power minus 4, then 3.15 raised power minus 5, like that. So talking about the rates now. So for I and range, so you have the length of errors minus 1. Then rate, you take the log of all that, like what we did. So error I plus 1, error 1, then over log again. So this is just us defining the function, and then print estimated convergence rates. Now you print the rates, and then so estimated convergence rate now you have 2.0 across board, like that. Then you can then plot the convergence plot. So figure, let's use the figure 7 by 5. Then you have log of H value errors and all that, and then you have mesh size H and L squared error and DG convergence study. So these are DG convergence study right here. Imagine as the mesh size becomes smaller and is it, yeah, I think it's getting smaller, right? Yeah, as it's getting bigger and bigger, actually, it's getting bigger here. The L squared error is increasing, like that. So that's the convergence study right there. Then we have number of degrees of freedom here. So for number of degrees of freedom, for n elements and polynomial degree p, the number of local basis functions in one dimension is p plus 1. Therefore, n degree of freedom is n into p plus 1. So for example, if n is 100, then for p equals 0, n degree of freedom is 100. For p equals 1, n degree of freedom is 200. So that's using this formula now. So for n is 2, so you have 2 into uh, n is 100, so you have 100 into 3, that's 300. So for p equals 3, so that's p plus 1, 3 equals 3 plus 1, 4, 4 times 100, that's 400, like that. And we have nodal and modal the discontinuous Galerkin. There are two major ways to represent the polynomial inside an element. So modal DG. So the solution is represented using polynomial modes. U sub h is summation over j of uj phi j. So legend polynomials are common choices in this case. Then for nodal discontinuous Galerkin, the solution is represented using values at interpolation points. So u sub h of psi is summation over j of u sub j L sub j of psi. So common nodal points include Gauss and Gauss-Lobato points. So both formulations describe the same underlying polynomial approximation, but their computational implementations differ. Then we have discontinuous Galerkin in multiple dimensions. So the one-dimensional conservation law, u sub t plus f of u of x equals 0, generalizes to u sub t plus grad of f of u equals 0. So sub x means you are differentiating f of u with respect to x, right? So that is this generalization here. So one element on an element k, the discontinuous Galerkin weak formulation becomes integral over, so I mean this whole expression you have right here. So here f of u is the flux vector, n is the outward normal. So f of u is the flux vector, n is the outward normal. That's perpendicular to f cap now. F cap is the numerical flux. So the one-dimensional interface becomes a face in multiple dimensions. So we can do discontinuous Galerkin in multiple dimensions. Then talking about a normal flux here now. Suppose f of u is f sub x u, then f sub y u of u. So for a boundary with outward normal, n is nx ny. So the physical normal flux is f of u dot n, which is f of f sub x u n sub x plus f sub y u n sub y. So thus, multidimensional discontinuous Galerkin repeatedly evaluates fluxes through element phases. So the fundamental idea remains unchanged. Elements communicate through numerical fluxes. So elements communicate through numerical flux. So this is the idea of normal flux now. So applications of discontinuous Galerkin, we've been talking about it a lot, right? So discontinuous Galerkin methods are used in many areas of computational science. Important applications include computational fluid dynamics, shallow water equations, atmospheric modeling, ocean modeling, wave propagation, electromagnetics, acoustics, elasticity, plasma physics, transport equations, reactive flows, geophysical fluid dynamics. Discontinuous Galerkin is particularly useful when high order accuracy, conservation, complex geometry, and local adaptivity are important. Then we talk about discontinuous Galerkin and artificial intelligence. We're in the age of artificial intelligence. In fact, artificial intelligence has been there all along. I mean, it was first coined in the year 1954 at a meeting in Dartmouth College, by some computer scientists and mathematicians, I believe. So, and we have an outburst, we have a boom in artificial intelligence these days. So let's see how discontinuous Galerkin also relates with artificial intelligence. Discontinuous Galerkin also connect naturally with modern scientific machine learning. So DG simulations can generate high quality training data for neural operators, surrogate models, reduced order models, physics informed machine learning, and data driven PDE solvers. And then, on the other hand, machine learning can also be used to improve numerical methods by learning numerical fluxes, closure relations, subgrid scale models, stabilization strategies, adaptive mesh decisions, and this creates an interesting bridge. Numerical PDEs leading to scientific machine learning, and scientific machine learning leading back to numerical partial differential equations. So we then also have discontinuous Galerkin versus continuous finite elements. I mean, we try to draw a difference, a little comparison initially, but this is a comprehensive one here. So talking about continuity, continuous finite element method, continuity is enforced, but in discontinuous Galerkin, it is not enforced. That was the initial parallel we saw. So in DG, it is not enforced. Continuity is important in continuous, but in discontinuous Galerkin, no. Then talking about degrees of freedom, the degrees of freedom are often shared in continuous Galerkin, but in continuous FEM rather, in discontinuous Galerkin, it is element local. So that means that each element has its own degree of freedom, and that's where we can have things like parallel computing happening. Then for numerical flux, it is usually not central in continuous finite element method, but it is fundamental in discontinuous Galerkin. So we need numerical flux here to ensure that information can flow from one element to the other. Then conservation depends on formulation in continuous FEM, but in DG, it is natural for conservation laws. So, and high order accuracy is true for continuous FEM, and it is also true for DG. Then for advection, it is advection. Continuous FEM is good with advection, and it is DG. Advection is excellent with DG. Then shock handling. Continuous FEM requires special treatment, but in DG, flux-based framework are required. Then for parallelization, it is good with continuous FEM, but it is excellent. There's excellent locality in the discontinuous Galerkin. So parallelization is excellent with the discontinuous Galerkin. Then for mesh flexibility, it is excellent in both cases. The number of degrees of freedoms, it is usually lower here, but it is higher here because every element can have its own degree of freedom. Then for implementation is complex for continuous finite element method, but it is more complex for higher order problems in discontinuous Galerkin. So these are um, some comparisons like that. Now let's talk about advantages of discontinuous Galerkin. The major advantage of discontinuous Galerkin is the high order accuracy. So large polynomial degrees can be used. So because of that we can have high order accuracy. And then locality. Most computations are element local. So every element has their own unique characteristics and features. Then conservation. Numerical fluxes naturally supports conservation laws. Then flexibility. Discontinuous Galerkin works on many types of meshes because you can have localized meshes in each for each element. Then flexibility. Discontinuous Galerkin works on many types of meshes. Then for parallelism now, the local structure is well suited to parallel computation because you can deal with each element on its own. Then adaptivity. Different elements can use different mesh sizes or polynomial degrees. Then for hyperbolic PDEs, this continuous Galerkin is particularly effective for transport and wave problems. So like heat transport and wave transport problems. Wave wave gen wave transmission, kind of. So talking about disadvantages of discontinuous Galerkin also has important limitations. For instance, you need more degrees of freedom. For the same mesh, discontinuous Galerkin generally has more unknowns than continuous finite element method. Then you have higher computational cost. Every element carries its own polynomial representation. So as a result of that, you need more computational power to do that. Then flux design. The choice of numerical flux affects stability and accuracy. Then there's shock treatment. High order discontinuous Galerkin can require limiters or shock capturing techniques. Then you have time step restrictions. Explicit high order discontinuous Galerkin methods can have restrictive CFL conditions. So then you have implementation complexity. A robust discontinuous Galerkin implementation requires careful treatment of basis functions, quadrature, element mappings, numerical fluxes, boundary conditions, time integration, and stabilization. Then we have the complete discontinuous Galerkin workflow here. For a conservation law, you have U sub t dot. So this is a generalization of the conservation law now. So just like the ut plus v sub x we had the other time equals 0, u sub x. So the discontinuous Galerkin workflow starts with the partial differential equation, and then you move on to you divide the domain into elements, then you choose local polynomial space, you choose test functions, you multiply and integrate, and then you do integration by parts, and then you introduce numerical flux, then you construct element residual, and then you assemble global ODE system, and then you advance in time and reconstruct solution and perform error and convergence analysis. So that's the summary of everything we've been doing so far for the discontinuous Galerkin workflow, step by step. So depending on the problem you're solving. So we have now 5 equations to remember. You have the discrete Galerkin approximation, U sub h slash k. So summation over j of uk comma j phi k comma j. Then that's the discontinuous Galerkin approximation we have there. And then, this is the phi talks about basis functions while u talks about what's that now? Trying to remember that. I've forgotten what that is. We saw it in the beginning. Then the jump, you have the jump. That's the difference between u plus and u minus. That's the values around the boundary. Then average, you have the average. That's 1 over 2 u minus plus u plus. Then you have discontinuous Galerkin for weak formulation. We are able to derive this from partial differential, from integration by parts. So we have this. Then you have the upwind flux, which is the same as the upwind flux. I think it's the same as not the central flux now. Okay, yeah, upwind flux is also the same thing as the Friedrich flux there. So you have F cap equals AU minus. Then together, these equations capture the core structure of discontinuous Galerkin methods. So this has been a very long ride. So so if you combining the flow and these equations, then we get what we need to get. Then the most important concept 1.42 1 point. Okay. Yeah, I was wondering. This is 1.43 because the last one is 1.42. This is 1.42. Yeah. So for the 5 equations now, this is 1.44, not 5, 1.44, then 1.45. So we have 1.45, then 1.46, 1.46. Okay, so quick. So we've seen 5 equations to remember. So this is 4-1. Yeah. So the most important concept in all is this. The central idea of discontinuous Galerkin can be summarized as follows. You have local polynomial approximation plus weak formulation plus numerical flux. So the polynomial approximation provides high order accuracy, and the weak formulation allows the PDE to be satisfied in an integral sense. And then the numerical flux communicates information between neighboring elements. Therefore, discontinuous Galerkin is high order local finite elements plus flux-based coupling. And then in summary, we have this that the discontinuous Galerkin finite element method allows the numerical solution to be discontinuous across element interfaces. So for a conservation law, u sub t plus grad dot f of u equals 0. So the discontinuous Galerkin formulation is obtained by dividing the domain into elements, approximating the solution locally with polynomials, multiplying the PDE by test functions, integrating by parts, replacing physical boundary fluxes with numerical fluxes, obtaining a semi-discrete ODE system, integrating the ODE system in time, then the key mathematical structure is this. You have PDE leading to weak form, leading to local polynomial approximation, leading to numerical flux and an ODE system, which can then easily be solved. The most important conceptual lesson is that the discontinuity is not a weakness of the method. So discontinuity is usually a problem in mathematics, but in this case, the discontinuity is not a weakness of the method. It is simply the mechanism that gives discontinuous Galerkin its combination of locality conservation, high order accuracy, geometric flexibility, and excellent parallel stability. So let's see the practice problems we have here now. So we have this practice problems. I think I'll try to solve two problems. I'll solve 9 and 12. So look at questions 1 to, you can see questions 1 to 8 clearly here. 1 to 8 clearly here. And then question 9, I'm going to solve. Question 9 says for a degree 2 discontinuous Galerkin approximation on the reference element, construct the mass matrix using the monomial basis 1 psi and psi squared. Evaluate all required integrals analytically. Okay, so let me snip this so I can just paste it on the work page. So I'm going to do 9. So I'll just copy this and paste it here. Okay, then I'll come back here. So the other one I'll be solving is 12. So let me also snip 12. A DG simulation using n equals ATP is 2 and blah, blah, blah. I'll also copy that. And bring it right here. Okay, so let's go for this now. Okay, let me show the rest of the problems. So here you can see up to 17, in fact, then the rest. So let's solve those two problems and call it a date. So here now, you have this for a degree 2. For a degree 2 discontinuous Galerkin approximation on the reference element, construct the mass matrix using the monomial basis 1 psi and psi squared. Evaluate all required integrals analytically. Okay, let's do this. So we know that for the degree 2 or the degree 2 discontinuous Galerkin basis, phi naught is 1, phi 1 is psi, then phi 2 is psi squared, like this. So, and then the matrix, the mass matrix is M sub ij equals integral from -1 to 1 of phi I, phi j, of course, of psi there, all of it the psi. So using symmetry, we have integral from -1 to 1 of psi d psi equals 0. So if you integrate this, we get 0 because the first layer it started with 1, right? So we have that. So using symmetry, we know that integral of psi d psi is this, and then integral from -1 to 1 of psi cube d psi will be 0. So we know that is settled. On the other hand, we have 1 psi and psi squared. So for symmetry, we have that. Then on the other hand, the remaining integrals, the remaining integrals, we then have integral from -1 to 1 of 1 d psi, that is equal to 2. Then integral from -1 to 1 psi squared d psi, that is 2 over 3. And that continues like that. Oh, I may have to move this down. Okay, let me try to move this down now. Okay, so with that in place, then we have done these other integrals now. Therefore, therefore, okay, okay, I need to get this off. So we also have the integral for -1 to 1 of psi raised to power 4 d psi. That'll be 2 over 5. You know, if you do this integration, you get 2 over 5. So you see, for all the odd ones, you get 0. But for all these 1, sigma squared, psi squared, psi raised to power 4, you know, we get 2, 2 over 3, 2 over 5, and so on and so forth. Therefore, we can get the mass matrix. Therefore, we have M to be 2, 0, 2 over 3. Then we have 0, 2 over 3, 0. And then we have 2 over 3, 0, 2 over 5. And that is the mass matrix we need right there. So the mass matrix, I guess we still need to move this one forward, down. So this mass matrix contains the inner product of the local basis functions and is a fundamental component of the discontinuous Galerkin semi-discrete system, like that. Okay, so let's go on to the next problem 12 now, which we have here. So a discontinuous Galerkin simulation uses n equals 80, p equals 2, with wave speed is a is 4, and CFL number c is 0.2. Using the estimate delta t equals ch over 2p plus 1 alpha, calculate the maximum suggested time step, like that. So maximum suggested time step. So here, first of all, we know that delta t is equal to ch all over 2p plus 1 multiplied by the absolute value of a. So that's settled. So, and then what other things do we have? So we now need h. H is 1 over n. So 1 over n, so that's 1 over 80. That is 0.0125. Settled. Then the next thing we need, so p is 2, right? We have p to be 2 right here. So since p is 2, since p is equal to 2, then we have 2p plus 1 to be 2 into 2 plus 1, which is equal to 5. So we have 2p plus 1 is equal to 5, like that. So now substituting the values, so into delta t. So we have ch. C is 0.2. C is 0.2. H, we got H, 0.0125. So that is 0.2 into 0.0125, 0.0125, all over 5 times 4, like that. That is 2p plus 1, that's 5 that we got here. And then A is 4. We have A here, which is 4. So, and then that means that delta t now, all together, if we compute everything, so the numerator is 0.0025 and the denominator is 20. So that means delta t itself, delta t is equal to 0.000125. That means overall delta t is equal to 1.25 times 10 raised to power minus 4. So this demonstrates an important stability feature of explicit discontinuous Galerkin methods, increasing the polynomial degree p. So if you increase the polynomial degree p, it increases the factor 2p plus 1, and therefore generally requires a smaller time, a smaller stable time step. And with this, we come to the end of this very lengthy special topic, which is the discontinuous Galerkin finite element method. So again, look at the problems and try following everything we've done. So from here, you can see questions 1. Okay, let me see if I can fit 1 to 10 at once. So you can see 1 to 10 here. Then we have 11. Okay, maybe not everything together. You can see 11 to 18 clearly here, and then the rest. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you haven't subscribed, what exactly are you waiting for? Why not go ahead and subscribe right away and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel. All right, you can become a member of the channel by clicking on join. that gives you some special privileges you see as you click on join. Ultimately, don't forget to comment, like, and share so that more people can have access to the great opportunity, the great content I have going on here. Till I come your way again, keep doing math right, and shout out to my school mother that requested for this. Bye.